Hi, welcome back. In this video, I'm going to talk about rational function applications, and specifically, we're going to look at the concentration of a substance over time. I hope this one will be kind of familiar to you. When you think of concentration, one example that might come to mind is dissolving sugar in water. So the more sugar you add to the water, the more concentrated it will become. And that's kind of the concept that we're looking at here. We would call the sugar the solute, and then the water would be the solvent, which is like kind of technical terminology, but kind of at the core of it, that's really what concentration is. And as far as units go, you're basically dividing solute by solvent. So the more that we increase our solute, the more sugar we add, the more concentrated it will become. And that makes sense because we'll have a larger numerator while the denominator stays the same. And so on our denominator is going to be that solvent, that water, I don't know, lemon juice, just any kind of liquid that's going to dissolve your substance. So I chose the units milligrams over liters, but there are a lot of different possibilities there. And so I'm going to get into the example here. So we have a vat that initially contains 7 milligrams of salt and 10 liters of water. At t equals 0 minutes, 9 liters of water flow into the vat per minute, while 1 milligram of salt is poured into the vat per minute. Find the concentration in milligrams per liter after 5 minutes. Okay, so our goal is to find the concentration, and we just talked about how we're going to take our solute, our solid, and we're going to divide that by our liquid or our solvent. And so you can kind of see on the right here, I wrote what that might look like. Our concentration function over time would equal our solutes over time divided by our solvent over time. And so in this particular example, we're comparing salt and water. And so if we want to find the total amount of salt and the total amount of water, then we want to take into account our initial value and our rate of change. So we were given some sort of initial values, and then we ended up adding some more of that, salt or water over time. And it's a constant rate of change, so we don't have too much to worry about. It's kind of just like a linear function, which we've seen before. And I'm going to go ahead and start with our water over time and see if we can model the total amount of water that we have. So we start out with 10 liters. Okay, and then we want to add our rate of change. So we have 9 liters of water per minute. So if we do 9 times t, that's kind of our rate of change. So we're going to add 9t, and then so every minute that we plug into our water function, it's going to give us the total amount of water we have. All right, so we have that. Whoops. Okay. Then we also want to model the amount of salt we have. So we start with our initial value, which was 7 milligrams. Okay. And then we are adding 1 milligram of salt every minute. So you probably guessed we're going to add 1t, which is just t. Okay. So now you can see kind of with what I have written in blue, we just have to divide these two functions, and now we have a model for our concentration. So if we do C of t, that's going to equal S of t, which is 7 plus t, over 10 plus 9t, which is our water function. And that's our concentration. And as you can see, it kind of looks like a rational function. So now we know how to find the concentration at any time. And so now we just need to plug in 5 for t, and we'll find the concentration after 5 minutes. So C of 5 is going to equal 7 plus 5 over 10 plus 9 times 5. Okay. And that's going to equal 7 plus 5 is going to be 12 over 10 plus 9 times 5. 9 times 5 is 45, plus 10 is 55. So I'm just going to leave my fraction as this, but it's going to be 12 over 55, or 12/55 milligrams per liter. Okay, and now I also want us to look at the graph of this function. So if we actually model this, I went ahead and plugged it in on Desmos. Now keep in mind, we can't have negative time, so anything to the left of 0 is not in our domain, but it's just kind of hanging out here for now. So on our y-axis, in our outputs, we have concentration, and then our x-axis is going to be time in minutes, and this is kind of what our curve is looking like over time. So here's one question. From t equals 0 to 2 minutes, is the concentration increasing or decreasing? If you want to pause now and try to think about that, then go ahead. Okay, is the concentration increasing or decreasing? So you remember that key feature from some previous videos. When we're talking about increasing or decreasing, we are looking at the sign of our slope. Are our slopes negative on that interval, or are they positive? And as you know, I like to use my little tangent lines. So we're looking at from 0 to 2. So let me see what my slopes are looking like. They're not super negative, but they are still negative slopes. So I would have to say my concentration is decreasing in that time interval. And then another question that's a little bit trickier is the absolute value of the rate of change increasing or decreasing. So, okay, let's break this down for a minute. The absolute value of the rate of change increasing or decreasing. Okay, so the rate of change, you can think of our slopes as rate of change, right? I believe I had that up here. Yeah, we had our initial plus our rate of change. And our rate of change, I kind of referred to a linear function, so that's just going to be like our slope. But I'm not asking you what the value is of the rate of change. I want to know what's happening to the rate of change. Is it increasing over that time interval, or is it decreasing? And so the reason I have the absolute value here is because at this point, I'm not concerned about the sign of my slope. I really just want to know kind of what's happening to the steepness. So whether it's negative or positive, are my slopes getting steeper, which would mean a greater rate of change? My rate of change is increasing. Or are my slopes getting flatter over time, which would mean that the absolute value of my slope is growing smaller. It's starting to get a lot flatter. And so in this example, we can see that we initially have like a pretty negative slope. You can see over time, it's starting to flatten out. So I think we can say that the absolute value of our rate of change or our slopes are decreasing over time. They're getting less and less steep. So if we're just looking at absolute value, they are getting closer and closer to zero. And it's okay if that doesn't make a whole lot of sense, but it's just kind of showing the difference between the sign of the rate of change and the trend of the rate of change. That's like a little bit of a difference there. But all right, so that's it for today. Thank you for watching.